Good morning, everybody. Today is basically the day after the exam. Hopefully, you guys have done well. I know probably some of you might have questions. Please defer those questions for private sessions. I know a lot of you are not actually today in, so the recording should be available immediately after class, hopefully around noon, so that you guys can also benefit from the discussion of after the class. And if you have any questions about the exam or anything else, please do ask it later on in messaging so that we can address those things. We still have another exam that is going to cover chapters 8 until I think chapter 11. So the chapter 8, we already discussed it last week. Chapter 9 is today. Chapter 8 was about electricity. Today is about magnetism. At some point in the development of these two branches, basically of science, a scientist by the name of James Maxwell, basically, Clerk Maxwell, he was able to combine the two branches of electricity and magnetism into one, and basically argue that electricity and magnetism are just two sides of the same coin, meaning that electricity can sometimes electrical phenomenon basically can transform into magnetic phenomenon and vice versa. And since some of you, or probably a lot of you actually are going to end up teaching in different levels of teaching, basically, especially sometimes in elementary and middle school, those students tend to be very, very inquisitive and ask a lot of questions. One of the questions that I have noticed is, what is magnetism? I mean, here is a piece of iron before me, okay? That if I bring another piece of iron that normally would not interact with anything, but with this one is going to attach itself to it. And no matter which way I let go of it, it's going to stick to it. As a matter of fact, this is so powerful, it's greater than the force of gravity. The force of gravity, remember that everybody is pulling on this pin. The Earth, especially being the supermassive object. But this magnet pulls it towards it, okay? No matter which way I do it, also it's going to pull it, whether up, down, side, on the other side. So this is a toy that almost every person, when they were young, they were playing with it. And it is really important to understand how this works, okay? How magnetism works. Now, magnetism by itself, it has a lot of applications in the daily lives. We would never have arrived to the advancement where we are right now in technology without magnetism. Think about it. Magnetism is behind every time you turn on the light. There's computers. If it were not for magnets, there could never be a power coming to your houses, coming to your factories, coming to your schools, coming to wherever you are, because that's how generators work. Generators of electrical power work. Not only that, not a single motor, electrical motor that is, would run without a magnet. So magnetism is crucial in terms of MRIs, also in terms of medical applications. That's very good. In terms of a lot of applications. So it's really, it is part of everyday technology and everyday experience that sometimes we take it for granted. It's not just a toy, okay? But it has a lot of applications in real life. Magnetism by itself, look at me. I'm holding it with my own bare hands and it doesn't do much. And like electrical charges, if I were to hold an electrical charge, you will see that it's going to be very dangerous, okay, for me, okay, or anybody. So magnetism seems to doesn't do a lot of effect, at least on this size. But on a global size, it's really plays a major role. As a matter of fact, the entire Earth is a magnet. We live in a big magnet, okay? If it were not for the magnetism on Earth, we would never be able to sit here probably and talk about it, because magnetic field of the Earth shields us from the radiation, the particles that the sun basically blasts every which way in the solar system. Because we're fortunate to live on a planet that has a powerful enough magnetic field that diverts those charged particles that leave the sun and end up in the North Pole and end up in the South Pole are those beautiful lights that you probably read about or have seen somewhere else. So that's basically the so-called northern lights and southern lights. That's basically what they are. So the magnetic field of the Earth is really a very powerful thing. I mean, it turns out that's not an exception. The Earth is not an exception. Almost all of the big planets have magnetic fields, especially Jupiter. Not so much for probably Mars, because it has a weak, I mean, it's small in size, so it does not have a lot of materials to generate currents inside of it, so to basically create a magnetic field. The same thing is true also for Venus. Venus also does not have probably very hard, I mean, big magnetic field because of the fact that it spins so slow. The day of Venus is so big, I mean, it extends for almost forever, okay? So that's really so the Earth really has a lot of properties that spins fast enough that we have a powerful magnetic field. So magnetism plays a major role. It plays a major role for us to be here to talk about it and everything else. It plays a major role in terms of our daily experience. And I personally have had a personal experience with magnetism when I was in elementary school, like anybody else, playing with my own magnet. And what I did with it, I put it on a spoon. On a very cold night, we had the heater going on. Actually, it was a super hot source because it was a very cold night. So I took the spoon, put on top of it the magnet, and I brought it very close from the fire. I didn't know what I was thinking at that time. I honestly don't remember. But the thing with it is, when I brought it back after it cooled, I tried to put it on the metal. It did not attract. I was so devastated with that. I thought something happened. So I cooled it, trying to think that's going to solve the problem of magnetism. It did not. So I asked my science teacher, and he basically told me that you must have reached something called the Curie temperature. I have never heard of such a thing. So that's what prompted me actually into science, trying to learn more about Curie. And it turns out she was one of the great scientists who ever lived and basically discovered that temperature. And by accident, I reached that temperature where I lost magnetism. So magnetic materials, like for example, this one, can be demagnetized by, for example, raising its temperature. And it can also be magnetized by putting it under a strong magnetic field and using a magnetic field in it. So basically that's the process. So that's in a nutshell what happened. I ended up being basically going to college, and after that going to grad school and doing research on the topic of magnetism itself. That was my thesis with one of the greatest scientists who ever lived in the field of magnetism. His name is Harry Soule. If you Google him, that is actually my thesis advisor on these things, okay? So, since you guys are lucky enough to have a person who have had first-hand experience with magnetism, so let's talk about it. And hopefully, by the end of the day, you will know what magnetism is, okay? And those students, especially middle school students and elementary school students too, they will ask you, what is magnetism? What is a magnet? Hey teacher, what is a magnet? And you should be able to answer that question, hopefully easily enough so that the students can understand you, okay? So, the topic of chapter 9 is on magnetism. So we'll try to talk about magnetic poles, okay? Remember when we discussed charges, when we were talking about electricity in chapter 8, we had something called a positive charge and something called a negative charge. Those, the fact that we call them positive and negative were by convention, okay? It's not like the positive is something has good in it and negative has something bad in it. It was just a convention, just to distinguish the two kinds. There are two kinds, basically. We could have called them different colors, red and blue, for example, or we could have called them right and left, or we could have called them up and down, or we could have called them basically whatever we would have to, just to distinguish between the two of them. The fact that we call them positive and negative doesn't diminish a thing from the electron or add a thing to the proton. It's just basically the fact that it was a convention, that's all. And the convention has to do with which way the direction of the current flows, that's all, okay? So once we chose the direction of the current flowing from the anode basically to the cathode of a battery, it turns out actually we made a mistake there. What actually moves were actually the electrons going from the cathode to the anode, And probably we could have, if we had thought about it a little better, probably we should have chosen the positive charge being the electron and the negative charge being the electron and the proton, and we would not be carrying so much negative, basically charges everywhere with us, because it turns out the electron is the most dominant particle in terms of our day-to-day experience when it comes to electricity. But that's just basically naming. So even if we have called it positive, it does not do anything to, it makes a little bit the math easier for us in terms of not carrying as much symbols that we would do. But in terms of meaning, they don't mean it. I mean, they're just classification of two different objects, that's all. So that's what I want to warn you on that topic coming from chapter 8. Same thing holds true in here for magnets. We're going to call something, instead of calling it positive pole and negative pole, we're going to call it a north pole. And another thing, we're going to call it a south pole, okay? So that's just to classify them. It doesn't mean that the North Pole has to do something with the North, or the South Pole has to do with the South. So for example, in this magnet, whatever its North Pole, let's say for example, this is the North Pole, this would be the South Pole, but this one actually pointing toward the East, and this one is pointing toward the West. So right now it's probably North and South. But right now, actually, if I flip it this way, it's South and North. The South is pointing North and the North is pointing South. So the fact that I call them North and South does not mean a thing. Okay, it's just basically convention to distinguish the two similar, identical, but opposite objects. So that's one thing that I want to warn you, similar to with the positive and negative. It reminds me of that movie, The Cat in the Hat. Do you guys remember it? Anybody have seen that? About Think 1 and Think 2? Okay, Jacqueline at least, okay? So yes, Think 1 and Think 2, you know, when he was basically argue, okay, Emmanuel too. So basically Think 1 and Think 2, they are identical, same thing, okay? So that's what I want you to really remember from this, is the fact that it's just a naming, okay? Just a naming of two things that we know for a fact have similar properties, except they happen to be two kinds of opposite side, okay? Of the opposite sides, that's all, okay? So that's one thing. And the other peculiarity, and this is a very important property, it's extremely important, you cannot really believe how much it is. It can always isolate positive charges by themselves or negative charges by themselves. It can always carry a negative 10 coulombs, for example, okay? I can always have a positive 10 coulombs or positive 17 coulombs by itself, okay? Isolated. The trouble with the magnetic poles is I cannot do that. They always come in pairs. That's really one of the things. So if I have a north, I must have a south. I cannot have a south by itself or a north by itself. That is one thing that distinguishes magnetism from electricity. So if somebody wants to know the difference between the two, one of them, the elementary properties that causes it are charges, namely electricity, and those charges can be separated. You can isolate them, okay? And you will have a charge by itself creating its own electric field, positive charge that is, and a negative charge way from it. It has nothing to do with the, I mean, as a matter of fact, I can move the positive charge whichever way I want to, and the negative charge would have, because it's far away, would not be really affected by what I do with the positive charge, okay? So I can always work with single charges with no problem. Granted, and that's true, that charges are conserved, meaning that the total number of charges in the universe doesn't change. So if I have 10 coulombs in here, somewhere else, I have probably negative 10 coulombs, or a negative 5 and a negative 5, or a negative 8 and a negative 2, combining for a total of 0. So if I have a 10 somewhere in here, I probably have some other 10 that is either together, negative 10 that is either together or split apart, okay? But at the end, I have conservation. But the point in here is that my 10 on one side, or my negative 10, or combination of some other chain numbers, is still can be isolated by themselves, and you work with them in the laboratory, and you have no problem with them. Granted, the positive 10 is sitting somewhere else on the other edge of the universe, okay? But my point in here is that I cannot do the same thing with magnetism. If I am in the laboratory and I have a north and a south pole, I cannot take my magnet and cut it in half and say, here, I'm going to take this north pole and I'm going to hide it somewhere else in a room, a next door room, and I'm going to work with the south pole. You can't do that. The minute you cut it in half, you end up with two new magnets, where this place where you cut it, this becomes the south and this becomes the north, and you end up with a new magnet in here that is north-south, and you end up with another magnet in here that is north-south. You cannot do that with magnets. You cannot isolate poles. That is a big difference between the two, okay? This is a huge difference between the two, okay? So you ask, okay, I want to do this. I'm trying to get into the bottom of this. Since I split this two, and now I have two magnets with north and south, I'm gonna take the smaller piece, it doesn't matter which, and I'm gonna split it halfways. I want to really get to the bottom of this. I want to find where the pole is, okay? So take this magnet, now I'm gonna split it into two pieces. So now this is the piece that I end up with. You're telling me I'm going to have a north and a south, be it. Okay, so this is a smaller piece now. This is north, this is south, okay? Well, I did not isolate the north and the south. I still have a piece, basically another smaller magnet, basically, that is north and south. I'm going to continue this process until at some point I would not be able to split this thing into two anymore. Basically, I come to the atomic level. At that point, if you cannot have a north and a south, you end up with nothing. So basically, you destroy your magnet. So that's really how the process experimentally can work. So that's really how impossible this thing is, at least from our daily experience. We're going to talk about poles. Okay. We're going to talk also about the magnetic field, which is similar to to an electric field. The electric field, if you guys remember, was produced by test charge, bring a positive charge, and now I have an electric field everywhere. This one is determined by a compass. Unfortunately, I don't have a compass in here, but basically if you bring a compass, you will see the needle points somewhere, the north points somewhere. The north, by the way, always points to the south pole, okay? So if you move it this way, it's going to point this way. If you move it to the other side, it's going to point to the other side until the south actually is pointing in here, indicating that the field is going around the magnet. So the properties of the field in here, in this case, are going to be like this. So the needle will point toward the south, always toward the south, okay? So this is what we call a field line, a magnetic field line. So I can trace it with a needle, okay? That was very crucial because the needle was one of the inventions that was from the early navigators. I don't know exactly who, probably the Chinese did invent that, is that it was used for navigation because it always points to the North Pole, okay? So from there, you can find your way. You just look at the North Pole, extend your hands, you know which way is east and which one is west, okay? So that's basically, if you know you came from east-west and you want to go back somewhere, so you can find your way more or less using that. That is, of course, if the stars were not available for us to guide us through the night. So that's one thing that is actually useful, especially during daytime. We can't really do anything, so we have to use a needle. So that's the magnetic needle, was used to determine the magnetic field. So the field lines are crucial in here because the more intense they are, the stronger the magnetic field, albeit right now I've been playing with a magnetic field that doesn't do much. There are instances where the magnetic field can cause tremendous harm. As a matter of fact, it's so powerful, it can really cause a lot of problem with the electronics and sometimes with even the physiology of people. Like, for example, one of the problems that the Huygens, the Huygens, Cassini, I'm sorry. No. Yeah, Cassini experienced, and also, Cassini experienced when it went to Saturn, was the magnetic field of Saturn itself. And then also Galileo's mission also to Jupiter also experienced some difficulties with the magnetic field of Jupiter. So they could be very, very damaging. And also let alone, for example, near neutron stars, which have very powerful magnetic field that they could basically flatten you, okay? We'll try to answer the question of what is a magnetic field right there and there, magnetic domains, okay? That is basically where the answer to the question lies. But of course, we should give a student, for example, in elementary school or even in middle school, a little bit simpler explanation than that, okay? Than the magnetic domains, because it turns out that it's a little bit heavy concept. It has to do basically with how the molecular structure, basically how the molecules come together and form different regions in materials, and those regions have specific direction for the so-called magnetization, and the sum of this magnetizations is what the magnetic field is. For most materials, basically like this bulk of thing in here that doesn't attract anything, that doesn't attract anything in here, it has also domains, but they are basically random every which way, and they cancel. But for this magnet, they somehow lean on each other, and they don't cancel. They add up to a finite value. Okay, so that's basically what the magnetic domains is. We'll try to answer the difference between a permanent magnet and an electromagnet and the effects of electricity in it. And that is the key to the answer to what magnet is electrical currents, okay? Mr. Ampere and other physicists did a lot of experiments with that, playing with electricity, and it turns out electricity causes magnetism, okay? Magnetic forces on moving charges. Again, this is the essence of motors, okay? So that's basically how the charges are being affected by magnetic field. Provided these charges are moving. If they are stationary, they are not going to be impacted by an electric field. So it seems like current, which is charge in motion, and moving charges play a role in magnetism. And that's why Mr. Maxwell, as I said before, in 1886, he was able to combine everything and put them together in a single synthesis, namely that magnetism and electricity are two sides of the same coin, okay? So that's in here. And then we're going to talk about electromagnetic induction, okay? How a magnet can induce a current in a wire. How magnets can create current for you. In other words, how Hoover Dam works, okay? You have the water falling, and as it falls, there is a turbine attached to it. As that turbine, for example, as that turbine is turning, the magnet inside of it is turning, and the magnet inside is turning, or the other way around, the wire is turning on the magnet. One of them, when there is a relative motion between wire and a magnet, current starts to run in the wire. And that current is exactly what the power company makes and delivers to us. Now, if you cannot have the turbine turn with water, you probably have a gas motor, gas basically engine, to turn the turbine for you and produce the same effect. On a bicycle, for example, you have that small dynamo that you attach to the wire, to the tire, and as you're pedaling, okay, you're also producing electricity, because now that thing also is turning inside the wire and producing your own current, which a light bulb that will light, okay? So it's the same principle, how to make electricity. And it's all due to Mr. Faraday's work, which is the how an electromagnetic induces a current inside a wire, okay? So that's basically another thing in here that is going to be discussed. And we're going to talk about the power production, which is a really critical thing. I mean, when the power company delivers power to your house, delivers current to your house, delivers electricity to your house, there's voltage to your house. That's all it does, okay? So the power company, when they connect your house or your building or wherever you are to their wiring, all they're providing for you is 120 volts per plug, okay? At that point, they really should not charge you. They are probably charging you for membership and taxes and all of the other nonsense stuff. But all if they're providing for you is the voltage, they should not charge you. The minute you plug in a device, your device starts consuming power, starts consuming energy at a single rate, at a certain rate. And that rate is the power. How much a light bulb will consume per second. For example, a 100-watt light bulb will consume 100 joules every second. So if you let the light bulb running for an hour, you have consumed 100 joules for every second, and there is 3,600 seconds in an hour. 3,600 times 100. That's, what is it? 360,000 watts, 360,000 joules of energy. Of course, they don't measure it that way. They measure it in kilowatt hours. Okay, but it's the same thing. Kilowatt hour is 1,000 watts per hour, which is 3,600. So it's an amount of energy. Okay. So that's basically how, when the power company starts to really charge you. And there is a certain number of cents per kilowatt hour that they should charge you. So that's really how this thing works in here in terms of the power company. And then we're going to talk about the transformers. There are two kinds of transformers. There is a so-called step-up transformers, and there is a step-down transformer. A step-up transformer is usually used by the power company to deliver power to big cities. So what they do in the, for example, the Hoover Dam, they take the voltage that is produced and they up it up to several thousands, tens of thousands of volts, and they deliver that to the power lines. It comes to your neighborhood with extremely high voltage. That's why there is a warning, high voltage, next to those power transformers. Now you have a step-down transformer that brings that voltage from super high down to your home at 120 volts, okay? So that is the step-down voltage. Now, your phone cannot run with 120 volt. So it needs its own transformer, because this phone runs on a 5.6 volts. My computer runs on an 18 volt. So 120 volts is too much. So you need another transformer, which is a device that you plug in into the wall, which is part of your power plug. It's basically for your device, for your computer or your phone. And that brings the voltage even smaller than 120 volts down to 5.6 volts. So again, for consumers, most of the time we deal with step-down transformer. For big power companies, they in order to deliver initially the power, they use a step-up transformer. Okay, and it's the same transformer. If you connect it one way, it's a step up. If you connect it the other way, it's step down. Okay, so whichever way you connect it. Although for safety and protection of your electronics, usually they have some specific devices like diodes and some stuff like that to prevent actually reversal of the transformer, to make the transformer only work one way. Okay, because there is some electronics that is on the other side that needs to be protected from the high voltages. So they cut the current, you cannot do it, okay? Or else it's going to burn, okay? Or else the fuses don't cut the current enough, early enough, then in this case, the whole thing basically is kaput, is basically disabled. It's no use anymore. So that's basically what we're going to be talking about. The field induction, again, is how to induce a magnetic field for different variations. And again, we're going, Mr. Ampere actually is the one who basically summarized the law of how an electric field creates a magnetic field. Mr. Faraday wanted to do the same thing. How is a magnetic field produces an electric field? It turns out Mr. Faraday was a little bit off. He found actually how varying magnetic field creates an electric field. And both of them work together. The reason why you can see at all, the reason why I can see at all, the reason why we have telecommunications at all with our phones and our everything else, that is signals that we send back and forth, is because of this play between magnetic field and electric field. And when they hit our eyes, basically an electric field creates a magnetic field, the magnetic field creates an electric field, and so on and so forth. As they leave the sun or as they leave another star, from that point on, there are no charges moving or stationary. Basically, they're in vacuum until they hit our eyes. At that point, the electrons in our eyes respond to the electric field, and that motion back and forth in the retina of the electrons is interpreted by our brains in terms of specific colors and specific intensities. It's a lot of fun stuff, isn't it? Any questions? This is basically the topic in a nutshell today. Could go home today. So let's delve into the questions, into the topics. Okay, let's get some stuff in. Thank you, Emmanuel. Okay, Again, this is the so-called, what is it, a horseshoe magnet, basically. Again, the naming convention, north and south, has to do which way the needle points, that's all. Okay, it's a convention. But there are two kinds, definitely, where the needle points from one way and points the other way to the other one, okay? It points up, if you paint in red toward what you call it north, where it points north, it points this way, and then when you look at it the other way, it's going to point with the other one, the one that is not painted. And that's how you draw the field line. You use a compass really to do that, okay? So we know that there are two kinds, and as I said before, we cannot have a one pole by itself. No matter which experiment you do, you cannot have a single pole, okay? In the 1940s, there was a person who claimed that he discovered the monopole, but it could not have been reproduced. No experiment after that was able to reproduce that experiment. So it's still not known that monopoles exist by themselves. Okay, because we can't think of a way of finding a monopole by itself. So no monopoles. Okay. So this is your first question of the day today. Can we isolate a pole by itself? The answer is no. There are no known monopoles, okay? Maybe scientists speculate, maybe if they exist there toward the edge of the universe, they already migrated toward the other side of the universe, but they don't exist where we are right now. So the physics that we have assumes that there are no such a thing. Did everybody get the first topic of the day today? Okay. Can we isolate a pole, magnetic pole that is, not a magnetic pole? The answer, of course, is no monopoles exist, okay? So that's what we know, okay? We can't. Did everybody catch the topic? Yes or no? At least the ones who are here right now. Okay, very good. So that's idea number one. There is at least another one that is coming. Thank you, Naomi. Thank you, everybody else. Okay. So magnetic poles, again, they come as dipoles. And they have this peculiar behavior also, that opposite poles, they attract, similar poles repel. If you take a north and a north, I have two magnets right now, they're attached to one another. If I pull them, they attract. If I pull them, they attract. If I reverse one of them, I reverse this one, and no matter how much I do, they cannot, okay, they repel. So that is basically a basic fact. Even I try very hard, they don't, okay? I was in a laboratory with one of the lab aides one time, and she told me that somehow they were able to create a state where somehow, they cannot, they always repel. That the north attracted the north or the south attracted the south. And of course, that's nonsense. So we tried to replicate what she said, because she said they did it with another instructor who was trying, because we have magnetizers and we magnetized one region and we brought the other magnet that is clearly labeled north, and it was attracting the south actually. So it was true north. And now we have a new north, and somehow now when they pulled them together, they attracted north to north. That is nonsense, I said. It cannot happen. The reason why this cannot happen is, the reason probably what they have seen, okay? This is my interpretation because I was not there with them. I'm not saying that it did not happen. I'm not saying that they lied or anything like that, so please. What I'm saying in here is that this is probably a so powerful magnet, the one that just magnetized, and the other one is a weak magnet, that this one managed to not only basically magnetize the other one, but to reverse the polarity on it. So this north that was weak north already was reversed and became a south for it to happen. okay? Just like, for example, if I take this piece of iron right now, it has no north or south. Try to put it next to any metal, it does not attract at all, okay? But now the fact that I bring a magnet to it, it's going to be attracted to it because I have induced a magnetic field inside of this one in here. So that's similar to it, except this one was actually magnetized, the one that they started with, had already a magnet. So if you see something that doesn't make sense with the physics that you know, there must be another explanation for it. Case in point, you cannot replicate it. I mean, if you try to replicate it, there is a probably justification for it. So before we abandon what we know is a fact based on experiment, based on the theories that we have so far, we really have to find alternative explanations. So you cannot tell me that somehow a north attracts a north. That is nonsense. That cannot be true. So something else must have happened in here where that powerful magnet that you just basically took off of the charger was powerful enough to induce magnetic field in the already magnetized but weakly magnetized magnet to reverse its polarity. So that now this is actually the south that was labeled north and was truly attracting the north before. I'm attracting the south before. So now this is actually, that's probably what happened. So yeah, I can believe that now, okay? Always try to find justifiable experience. Some students will ask you this question, so you have to be ready for this kind of things. Some people will always be confronted with these situations. Do not be ready to abandon what you know for a fact until you basically run out of explanations, run out of theory for it, because unless you reproduce it again and again, like the guy, for example, who claimed he was able to who was a scientist actually, to claim that he was able to isolate the monopole, if his experiment was reproduced somewhere else, then we could go back to this thing in here and we change the answer. And then the prompt of the day will be different. You guys understand what I'm talking about? What the fuss is all about? It's about the scientific method, actually. It's not about the monopoles or it's basically you have to be really scientist in your approach. You have to really redo the experiment and again before you change your theory. Okay? So again, it drops with the distance, also similar to the electric forces. So far, so good? Everybody? Yes? Easy enough? I need a reaction from you guys. Should we continue or not?
Yes.
Okay, thank you, Naomi. Thank you, Sarah. Okay, so again, the magnetic poles, north and south, they give rise to the magnetic force, okay? And there are two types of poles, as I said before, a north pole and south pole, okay? And a rule of magnetic forces between poles is like poles repel and opposite poles attract. So that's basically how these things are in terms of behavior. Here is an interesting question. Weak and strong magnets repel each other. The greater repelling force is by, this has nothing to do with magnetism. This has to do with the third law of Newton, okay? Since they're interacting, it doesn't matter which way, that's what the third law of Newton says, the two forces must be the same, okay? Albeit one of them is a weak magnet, the other one is a strong magnet, the fact that one of them is repelling the other one is repelling with the first one with the same amount of force. Otherwise, we have a flaw in Newton's laws of motion. So this is actually per the third law of Newton. Okay? So that's why. If you have two interacting, one being strong and the other one being weak doesn't mean a thing. Like, for example, the Earth is pulling on me right now by about 700 newtons. That's 70 kilograms times 10, which is about 700 newtons. I am pulling also the entire Earth with the same force. So don't take me lightly, okay? I can pull the Earth, okay? And you on it too. So that's the third law at work in here. Of course, you guys do the same thing too, so don't feel bad, okay? You have the same power. Okay, so the magnetic field lines, how can we find them? I mean, there is a very nice experiment in the lab. Unfortunately, we don't have access to it, using the so-called iron filings that you drop and basically around the surface, and you put the magnet underneath a piece of paper, and you will see this nice picture in there. As they line up along the field lines, and you draw these field lines. Actually, the image picture itself will have those things in there. So basically, again, you just go with the needle, as I said before, and you trace the magnetic field going from one side to the other. Where it is, the field lines condense, that's where the stronger the strength of the magnetic field is higher. Okay, this is one of the things that causes damage on Earth. Is this? If you look at some of the pictures of the sun, those big basically solar flares, the way they form is actually by having the circulation of the charges on the surface of the sun creates basically a pole, and the opposite side is another pole. And now you have the charges on the surface of the sun that form a big arc. And those arcs, sometimes they extend for millions of kilometers, basically outside of the sun. So they are very big, very huge. Sometimes they snap. In doing so, the charges that were supposed to come back and fall on the sun actually end up being freed and goes every which way. And they could cause a lot of damage. Actually, they're one of the things that we're looking for all the time, trying to monitor, because they could cause an technology-ending events that could disable every single electronic and electrical device on Earth. So those things are pretty dangerous, and they're coming from the field lines again that they form around on the sun surface itself. But if they go around and don't cause any snap in them, because the sun actually is spinning too, if they behave nicely, we don't have a problem. But if they snap, and they do while they're coming down, and the charger that they have in there freed up, and if we are in the right direction where that happens, because they happen all the time, it can cause a lot of damage on technology in here, and basically we'll end up back to the dark ages. Okay, we have no motors running, nothing, no watches, no nothing. Okay. So again, magnetic fields produced by two kinds of electrical motion. Again, in here, the key answer to what a magnet is that the motion of the charges, specifically that of the electrons. Okay, those are the one that causes magnetism. So charges inside the particle, inside every single object, they move. That's because of all kinds of phenomena. They have to move, otherwise they will fall on the atom, and then the atom will not be stable. Okay, so they have to move. Okay, and while they're moving, because now their charge is in motion, they create their own magnetic field. Okay, same thing actually happens with the protons inside. They create their own magnetic field. And as a matter of fact, the spin, which is a property of elementary particles, is a fundamental property. Even neutral charges, like for example, neutrons, do have it. But the main player, even in magnetism, are actually the electrons. And the electrons have two kinds of motions. They either spin around their orbit, okay, going around the atom, around the nucleus, or they spin around themselves, their axes. Similar to how the Earth behaves. The Earth, when it goes once around the sun, that's a year. The Earth also goes around its axis, that's a day. So the Earth has two spins, two rotations. One around its own axis, which is once every 24 hours, and that is day-to-day experience. And then we have the rotation around the sun, which takes a year. This is similar to the case of the electron, okay? So the electron also has this motion around the nucleus. That is an orbital motion. That has something called the moment. And then also it has an internal spin, which is very hard really to explain, okay? Because an electron is a point particle, but for some reason it behaves as if it's spinning. So we really don't understand, honestly, the motion, because it really involves another branch of physics, which is a little bit more advanced, which is called quantum mechanics. But again, that's basically in a nutshell, similarity, if you wish, okay? So don't take it verbatim that this is exactly the motion of the electron around the nucleus is similar to how the Earth moves around the sun. But similar approximation, if you wish. It's a model, okay? So as every electron is doing that, they're moving around that one, they're creating their own magnetic field, okay? But the magnetic field now, some atoms are pointing this way, some atoms are pointing this way, some atoms are pointing this way, some atoms are pointing that way, some atoms are pointing to you, some atoms are pointing to me. So on average, most of the materials, this spins, if you wish, they're random. So if you add, for example, a -5 plus a +5, a -3 plus a +2 and a +1, at the end, you're going to end up with nothing. You're going to end up with 0. So that's basically what most of the materials do. But in certain materials, entire regions actually have this structure. Some regions are bigger than other regions. Some regions, they all work together in one direction, more or less, okay? Some other regions, no. They have smaller regions and bigger regions, but they're opposite, okay? They're in opposite directions. So as you can see from these arrows, for example, I'm going to pick at random just this region and this one. They seem to be almost canceling. There is a tiny one, but that's fine. They seem to be canceling. Take, for example, let me take another color in here. This one and this one. They also cancel. On average, if you take a big enough chunk of material, these domains are very tiny, by the way, very, very tiny, microscopic actually. So overall, if you take a macroscopic level, if you take a big picture of it, you'll find everything is canceling everything at some point. There is nothing in here that is, I mean, here, for example, this region in here and this region, they seem to be opposite to one another. And this is true for the entire bulk of the material. So most of the time, this random distribution averages to 0. However, in certain materials, like, for example, iron, that's one of them. Cobalt, that's another one. And nickel, that's the third metal. These 3 metals have a property where sometimes these regions tend to help one another and stay more or less in the same direction. That's what magnetism is. So that's the question of the day. What is magnetism? Magnetism is due to the motion of charged particles. A permanent magnet, which is a magnet has joining regions staying in the same direction. Their magnetization is in the same direction. This is the magnetization. So let's answer that. But for a student who is in elementary school, magnetism is due to currents. Okay, that's one thing, like an electrical current. Or, if you wish, moving charges. That's what a current is, moving charges, okay? Or, and permanent magnet, that's a magnet, the day-to-day, what we say magnet, that's a permanent magnet, has joining regions pointing, magnetization, the word for it, okay? Magnetizations pointing in the same direction, okay? Non-magnets, and this could be true for iron and nickel and cobalt too, where they are not magnetized, okay? The same material could be magnet or no magnet. Non-magnets, regions cancel on average. Okay, they have a word for this regions called domains, okay, magnetic domains. So that's the answer, more or less, of what a magnet is. I know it's a little bit kind of the key point in this answer is the fact that it's due to currents, due to moving charges, okay? That is the key answer to it. If you want to delve into the details are in the 2 sentences below that. Does everybody understand the second question of the day?
Yes. So would we be saying that magnetism is due to currents with moving charges?
Currents actually is moving charges.
Okay.
Yeah, Naomi, but the question for you now is not that. The question is, how come this piece of iron has a magnet and the other piece of iron doesn't? And the answer is in the last 2 sentences.
Okay.
Okay?
Yeah, I got it. Thank you.
Okay, no problem. So the first question has to do with what, and the second question has to do with what? The first question has to do with the monopoles. Can we isolate monopoles? No, we can't. Okay, at least that's what we know. The second question is, what is magnetism, or what is a magnet? The answer is magnetism. First of all, is due to moving charges. The same piece of iron can be magnetized or not, depending on the regions, joining regions, help one another, okay, or not, pointing in the same direction. Okay, so that's really the answer to the question. Okay, does this make a little bit of sense? If you want to be technical, these regions are called magnetic domains. Okay, Sherry, we're going to say something other than approve?
No, sir, I was just answering your question.
Okay, very good, thank you. Okay, so let's continue now. So again, this is basically the same thing that I was saying in here. This is now the entire region is working together. That's what the experiment I was talking about in here. This is a magnet, you cut it in half, you still have another magnet, and so on and so forth. That's what I was talking. That's the first question actually of the day. Okay. Again, this is due to Mr. Faraday, Mr. Ampere, I'm sorry. If you run a current through a wire, now, without any magnets whatsoever, forget about magnets, okay? I have this wire actually in here for you that I used to do. If I connect a battery in here, the current will start running through this wire, and the same bar, the same pin that was attracted to a magnet will be attracted now to this wire. If I cut the current, there is nothing in here, no magnetism whatsoever. So this seems to indicate what I said before, that an electricity, a current running through this wire really creates a magnetism. So that's how we know. So currents create magnetism, okay? The same thing in here. Put the needle next to a wire, and if there is no magnetism, no current, I'm sorry, the needle can point whichever way. I mean, it points just to the north of the earth. The minute you connect the wire to a power source, battery, or anything like that, you see the needle change direction, respond. Okay? So that's why magnetism is caused by currents. And this is the model for it, okay? Whichever way the current is going, the needle will go. It goes per the right-hand rule. So if you're left-handed, you're out of luck. You have to still use your right hand. So if the current is going with your thumb, the magnetic field is following basically your palm, okay? So this is, so if you're doing the left hand, it's not going to work. So forget the left hand, okay? So you have to use the right hand. So whichever way the current is flowing, this is basically your thumb. The magnetic field is going to curl around it, following your palm. So if, for example, it's going up, it's going to curl clockwise. It's always clockwise, okay? So if it's going to the east, it's going to curl away from the screen towards me. If it's going to the west, it's going to curl away from me toward the screen, okay? You guys understand now? This is the right-hand rule, okay? This is the right-hand rule. So even if you're left-handed, you can't use this. You have to still use your right hand, okay? This is the same thing as I was explaining in here. This is the current. Now this is current, now it's flowing this way. So again, when it's coming out of the screen, when it's around the screen, and what's going back into the surface. The same thing in here. This is actually the same wire running back and forth. This is the solenoid. This is similar to what I have in here, okay? So if your car, for example, has a problem generating current and you go to change your alternator, or what is it? Yeah, the alternator, that's what they sell you. That's what they give you. They give you a wire wrapped around so fast that it's going to basically create current, generate currents to your battery so that it keeps it charged. Okay. Okay, this turned out to depend on the number of turns. I mean, you don't see it very close, but there are so many turns in here, and it's thick, okay? So it depends on the number of turns. The strength of the electric field of the electric magnetic field that is generated depends on the number of turns. Number of turns. How many turns do you have in here? You have 1 turn, or 2 turns, or 3 turns, and so on and so forth. That's basically how many the coils that you're going to form in there. And of course, the current. The stronger the current, the stronger the magnetic field. If you have no current, you have no magnetic field. So it depends on N, the number of turns, and of course the current itself. Okay. How many times, how often does the current go around? That's basically what you're saying in here. So the answer for this one is both. Now, magnets interact with moving charges. Magnetic field specifically interacts with moving charges, and it follows actually the right-hand rule too, another kind of right-hand rule. This is the charge moving this way, okay? And if the magnet, for example, is pointing up, then the force in this case is given by the right-hand rule again, but another one. This is the direction, the thumb follows the direction of the moving charge. If it's a positive charge, if it's a negative charge, you have to flip it, okay? So if it's a positive charge, it's moving this way. This is the direction of the magnetic field. The force now follows where this finger is going to point. So in this case, the force is going to come out this way. So again, you go like this with the right-hand rule, okay? Don't use your left-hand rule. Have you guys seen rappers and how they sing? Yes? Rap music? Anybody? You guys are not into, you're all classic music people? No?
I'm not a classic music person.
Rappers, they use the right-hand rule too. So please, if you're going to learn anything from rap music, learn the right-hand rule. That's how you find also how the force points into it.
I'm not really into rap either.
Well, then if you are into physics 1, physical science 1, you have to use your right-hand rule, okay?
I'm really, really not into physics at all.
Well, if you're going to pass this class,
I'm struggling.
If you're going to pass this class, then you're going to use the right-hand rule. How is that?
I'll remember that.
Okay, very good. So again, depending on which way the current is flowing, namely which way the charge is, in this case in here, it's going to point up or down. Remember, the charges in this case, for example, are moving this way. The magnetic field is pointing this way. So again, if I use my right-hand rule, the force is going to be that way, okay, upward. If the current is flowing in the opposite direction, the magnetic field is still pointing this way. So in this case, if I use it, it's going to be pointing downward, okay? So there is a definite direction for this one in here. And magnetic field, of course, is used in this case for levitation, for lifting objects, okay? You have currents running through the trails, and you have magnets inside the train. So the magnets now and the trail, they will interact with this force that we just were describing and lift the train off the track. So the trains in Japan and Europe, actually the what do you call them? The TGVs, they're actually running, they're flying, okay? They levitate, but before they come to the station, they slow down the current enough for it to come back to the ground and have more friction to slow it down, okay? So that's some of the benefits of that one. The Earth, as I said before, is a big magnet, and it protects us, okay? Deflects many charged particles that make up cosmic radiation, not just from the sun, even from the rest of the universe. So in a sense, it's the Earth magnetic field that basically shielded life on Earth from going extinct because of the magnetic field again that deviates particles. Same thing, the particles that as they're coming through from space and they find a magnetic field, actually they spiral. So if there is a charge that's come from the sun, it's going to spiral toward North Pole if it's a given positive charge, for example. And if it's a negative charge, it's going to spiral down to the other side. And at the end, the rest of the Earth is protected from that, okay? When they reach the atmosphere, they produce this beautiful lights, okay? the magnetic force on a moving charged particle can change the particle's direction, like for example the case of the charged particles that come from the sun. Okay, they're heading straight to Earth, but the magnetic field now serves as deflecting those charges to some other places. Again, devices that use, for example, the properties of electricity and magnetism, they can be used as measuring devices, for example, the current. If there is a big enough current in here, the needle will swing more than if there is a weaker field, a weaker current. So that swing can be actually labeled correctly and basically gauged depending on the strength of the electric field in here that caused it. And that electric field could be, for example, due to a gradient in temperature or something else. So this could be used for all kinds of applications. Okay, again, in here I have some ammeters and some voltmeters that are used to measure electricity, whether current or voltage. Okay. And in here, this is the electric motor. In this case, what you have a permanent magnet, and you have a wire in here, okay, that has a current in it, okay, that has a current flowing in it. As the current flows now through this one, the current that has moving charges in it again, and the magnet, they interact. So what happened in here in this case is the magnet want to turn the loop in such a way that its magnetization aligns with that of the magnet. So basically it does the same thing, the right-hand rule on it too, again, to cause it to move. Once it reaches the other side, there is actually, in here, there are brushes that free this loop. And because of the momentum, because of the kinetic energy that it has already, because it's moving, it's going to move in the opposite direction. And now the current, as it changes direction, will continue to basically, I mean, this is a permanent current. This is going to change the direction and now will force it to move one more time. So it's going to have it move around and around and around in a circular motion. So that's the principle of the motor behind it, okay? So you have a magnet and a current. And the current is usually provided by battery, electrical battery or power source or something like that, okay? So that's how the motor is, whether it's powering your fan or it's powering your dishwasher or anything else, or your car. It's the same principle, okay? For electrical cars, that is 100% electrical cars. A similar motor and generator are similar in a sense. They play reverse roles, okay? One of them uses electricity to create motion, and that's the motor, taking electrical energy and converting it into an energy of motion, the fan moving around, or the generator, which takes the motion, which is, for example, due to the fall of the water, and converts it to electricity. So they work almost opposite to one another. As a matter of fact, their engineering is not different from one another, okay? So again, this is the electromagnetic induction. If you have nothing at all, okay? You have no current, you have no battery whatsoever. So what you do in here, that's Mr. Faraday's dilemma. He wanted to basically see which way a magnet can create a current, and he noticed that the motion of the bar magnet versus that of the loop that creates a current. Now that's how we can make a current, okay? So that's the experiment of Mr. Henry and Faraday, okay? There's a funny part in here with Mr. Lenz being involved with the experiment. Mr. Lenz add a minus sign to it to indicate the direction of the law, and from that point it was named also after him too. So again, it really has to do with something called the magnetic flux. If the flux increases or decreases, if it changes, then in that case you have a current that is created in the wire. Now this could happen in the opposite way. This is moving the magnet on a wire in a loop. You could move actually the wire inside the magnet too, and it produces the same thing. You will see the needle move, indicating that there is a current. You will see actually the ammeter indicating that there is a small current moving around. So either you move the magnet in and out, or you move the bar, the actual loop in and out. You're going to have the same thing. You're going to have the same effect. okay? So again, the number of turns play a role in here too. We still have quite a few minutes in here to finish this, so we'll probably have to expedite a little bit in here. So this is Faraday's law. The induced voltage or in a coil is proportional to the number of loops, so how many turns you have, like the example I was showing earlier, and multiplied by the rate at which the magnetic field changes within the loop. And that magnetic field changes can be due either to the magnet moving or to the loop moving, and that's really an engineering issue. Would you want the wire to move if you're going to build a generator, or would you want the magnet to move depending on your design? That's basically how you're going to tackle that, okay? You're going to have the same thing. Again, it's really a frictional effect. You can use that to slow down the motion using this effect, because it's really, if we did this experiment, actually I bought one from Amazon similar to this one, but it's a very long one where actually if you let go of an object, it's going to fall straight out without force of gravity, but inside a magnet, it's going to slow down because it's going to induce currents, which are called the eddies, okay? Or eddy currents, okay? Due to Mr. Faraday's law. Again, that is really what the resistance we're talking about. The currents that are induced in the metal in here as you're moving them in and out, that's basically what you're going to experience. Because that law that I mentioned earlier for Mr. Faraday, as I said before, Mr. Lenz is the one who explained the direction of it. And this explanation has to do with the resistance, basically, to the change, okay? In other words, the changing flux induces a magnetic field inside a wire, and that magnetic field will induce its own magnetic field to oppose the changes that created it in the first place. And that opposition, basically, it's like it bites the hand that created it, okay? And that opposition is this so-called inertia in this case. That's where the resistance is coming from, okay? The resistance you feel when you're pushing on a piece of iron into a coil involves repulsion of magnetic field, because now you have the magnetic field, the magnet that you're pushing in and out, and the induced magnetic field in the wire, because now the wire has a current running through it. So it's going to create its own magnetic field, again, by Mr. Ampere's law, the one that we said that currents create magnetic fields. Since now the magnet creates a current, that current that is running in the wire will have its own magnetic field, and that magnetic field will oppose the first magnetic field, and that's what you feel as a resistance yourself, okay? So that's really how this can be explained. Again, this is the generator. It's the mechanical motion now that create the same brushes actually are in contact with the loop in here. They're going to create the current now. So in the first picture, if you notice in the motor, what you have a wire connected to a battery, connected to charges. That creates motion. This thing moves, and now you have a motor. And the picture in here, it's the opposite. You have a motion, manual motion, for example, in here, generating electrical current in here. So that's basically what the difference between a generator and a motor is, okay? Which brings us to a transformer. Transformer is a useful device because the power that you have in your house, 120 volts, which is really between 170 and negative 170, but on average, it's about 120 volts. That's the effective voltage that you have in your plug. It's too much for most of your applications. Basically, almost everything, your TV or your refrigerator actually needs a higher voltage. Some of the refrigerators, they require some higher voltage, up to 240 or something like that. So they require higher voltage. So they need actually step-up transformer there, or you need to change the connection plug there to allow for that. So most of your applications are the so-called step-down transformer. So you have the so-called primary. The primary has a certain number of turns. That's usually different than that of the secondary. Again, like I said, the primary and the secondary can reverse roles in here, okay? So because step-up transformer can be step-down. So what I call step-up transformer in here, that means the number of turns in here. Let's say, for example, it's 100. And in here, let's say, for example, is a 10. This would be a transformer that takes 1/10 of the voltage. That means it's step down. If I connect the primary here, I have 120 volt, I will end up only with 12 volt at the end in here, okay? Whereas if I connect it backward, if I connect 120 volt in here, I will end up with 1200 volts in here, okay? So the primary becomes a secondary, and secondary becomes a primary. So this is a picture of a transformer, typical transformer used to look like. Now they are much smaller and they look different, but still, they are made up of a primary and a secondary, which is magnets with wires wrapped up around them, okay? This is the transformer relationship, the primary voltage over the secondary. That's what I used earlier for the formula, by the way, okay? So I had put 120 here. No, I put it a bit backwards, I'm sorry. I put 120 here. And I assumed that this one has 100 and this one has a 10. So in order for me to find the ratio of 120 over 10, I needed 12 in here, okay? So that's the relationship I used there earlier in the discussion that I was giving the example there. Again, both of them are step-down transformers, okay? Both of this is charger of some sort of your device. That's actually transformer because it's taking 120 and going through this wire, connecting it through USB device directly to your phone or your device. And that is really if you read very close on the specifications in here, it will tell you exactly what is the output. It will tell you the output voltage and sometimes tells you the input voltage that it has to be the US connection, okay? And this is for an application, an industrial application where it's taking it to your neighborhood, okay? Step-up transformer and electrical circuits can step up voltages, okay? You cannot gain energy out of nothing. You cannot, because if it's step-up energy, that means we're getting energy out of nothing. And this violates one of the principles of physics, actually. You cannot get energy out of nothing, okay? So this cannot be true since one of them is not, and since we know the voltage is correct, okay? Which brings me, like I said to before, is the power. The concept of the power is how much you're going to be charged every second, and it's really the voltage times the current. If you look at the transformer, the specifications of any transformer like this device, for example, in here, it will tell you not only the output voltage, but also the output current. Multiply this two, and you will see how much power your cell phone, for example, is going to take, or your computer is going to take. And if you let that device plugged in for a long time, actually my computer is charged now, so there is no need to keep it connected. You will see that it's basically going to consume how much power it's going to consume at that time. So it's again, voltage times current, okay? And this is the industrial applications again. This is basically a step-up transformer somewhere in here. Take it through the power line, come to your neighborhood, bring it down a little. This must be a step-down transformer to deliver it. This is coming to probably a big region, and then in here it's going to be distributed in your neighborhood. So that's basically how this. And now this is the expression that I already, in terms of power, again for a transformer, it does not make up power, it does not create energy. The voltage times current in the primary, which is the power in the primary, must be the voltage times the current in the secondary. Even the transformer does not create energy. As a matter of fact, because it heats up and try to touch a charger that has been plugged in for a long time, when you touch it firsthand, usually you find it warm. So it actually loses energy in the process. It's not gaining energy due to heat, okay? So again, this is the idea I was talking about earlier. Let's say, for example, you have an electric field that left the sun or a star, okay? And a magnetic field. At some point, they will start working to create each and every one of the other. A varying magnetic field will create induce an electric field and vice versa. And this is the so-called EM field, electromagnetic field, okay? And that's how signals are transmitted, because both the electric field and the magnetic field, which are part of the EM field, they are only one side to the other. Two sides, I'm sorry, to the same coin, okay? And that is actually the discussion that we have. I mean, that is actually all the stuff that we have for this chapter. And you have 2 questions, so please try to answer them and have a discussion that is interesting for all of us at the end of the day today. Any questions on chapter 9? If no questions, then I'll guys see you Tuesday. You have a question, Sherry?
No, I just want to make sure. Was there only? There's 3 questions, right?
2.
2. Okay, I think I have them. What is magnetism, and can we isolate a magnetic pole? Right?
Yep.
Okay.
That's it. Okay.
Right, just checking.
Okay.
Make sure I didn't miss anything.
Okay. So don't forget, I think we don't have a lot of assignments this week because we have had just our exam. So
Thank you.
week, yeah.
Thank you for that. There's a lot of reading, a lot of studying, and
okay. Yeah, next week, this exam is going to be a little lighter. Since we're not talking about the class, so I mean about the chapter, so I'm going to stop the recording. Or probably we can keep it, maybe it benefits other people. Anyway, the point being is we still have exam 2. Now exam 2 is a little bit lighter than exam 1. So hopefully it's going to be a little less load for you guys than the first exam. And the third exam actually looking to focus mainly on chemical processes, chemistry basically, okay?
Oh, goody.
Okay, so I'll see you guys Tuesday at 8:30 and watch for the announcements over the weekend in terms of basically the next chapter, and that's chapter 10. And then after that, we're going to have another chapter and then our exam.
I just have one last question. So grades, when will all our grades be coming in?
Aren't they coming in? They're
No.
Hold on.
Like homework, our participation, all the stuff we've been, discussion boards, all that are not graded.
What do you mean? Hold on, let me check exactly. The dates that are up to last week, they're all graded. Hold on, let me check. Then it's a problem in here if that's the case. Hold on. Okay. Okay, exam 1 is done. Homework 2 is, okay, that's due. Okay, homework 2 is not graded. You're right. And when was that due? Okay, so that will be graded this weekend. It was due last weekend. So it's the 19th. So that's still this week. So usually it's within a week time. Okay, the other things are graded. This chapter 5 discussion. Oh, that's when was that due? That was also last week. So that's going to be due this weekend. Hopefully I will get around them. So you're right. There are quite a few that were due last week. And usually I have this time around that I have to turn things. So chapter 6 and 7 also discussions. Okay. And so we have 3 chapter discussions and a homework. Okay. That were due last week or more or less. And they should be graded this week. Everything else is graded. Chapter 8 is still not due yet, okay? Chapter 8 is still cannot be graded until a week after this week. Okay, it's still actually due the 26th, so I cannot grade it before everybody is done with it, okay?
Okay.
Yeah, so that's where we stand. I think usually within a week time after the assignment is due, I will usually around weekend when I go around them and get them graded. And this weekend was actually busy for you guys setting up your exam and setting up some other class exam. So that's why I didn't catch up with some of the stuff that was actually due last week. But usually within a week, they should be done. They should be ready.
Okay, thanks.
No problem.
Okay.
Okay. See you guys Tuesday then.
Have a good weekend.
Thank you. You too. Bye.
Have a good weekend.
Okay, you too. Bye.
Have a good weekend.
You too. Bye.